Let's just begin to look at chemical equilibrium. So we'll move from the basic concepts of chemical equilibrium, breaking it down one by one until we get to look at multiple practice questions on this topic. Okay, so what is chemical equilibrium? When do we say a reaction is at chemical equilibrium? So whenever we're talking about equilibrium, it is very important that you get to understand the concept of reversible reactions. So we'll consider a case where we have A reacting with B to give us C and D. And then let's take some coefficients here, stoichiometric coefficients, using their small letters. So if you look at this kind of a reaction, we've got a full arrow pointing on one direction. So it shows that these are reactants, those are products. Okay? Now for a reversible reaction, there's something that changes about it. So try to see what's going to be different. So you have something like this, half arrows, one pointing to the right, one to the left. What this tells you is, of course, initially you may start with products A and B, but after time has elapsed, you find that there will also be a what? A reversible reaction. Of course, A and B are referred to as reactants. So your A and B in this case are reactants, and then they give you products. Now, after time has elapsed, you find that there also be now a reversible reaction which will involve the products as well reacting to give you back what? The reactants. Okay? So these will be occurring at different rates. The rate at which C and D is forming is going to be different from the rate at which A and B is being formed back. So what I've said is you've got A and B reacting to give you C and D. Initially, after some time, you also get to have both now. C and D also reacting. So it's like A and B reacting to give us C and D, and then D is also reacting with C to give us A and B. So it starts, if we are to have a graph to describe what is basically happening, remember at start, all you have is what? So let me do this. We'll take this to be the concentration, and then we'll take this to be the time. So as you start, you realize that you're starting with the concentration of the reactants higher, and after a certain time, the concentration will be reducing after time. Now, you realize that the concentration of the products will be increasing after as time increases, okay, until they get to be more than what? Until they get to be more than the reactants. So the green line is representing the product, and then the other one is representing what? The reactants. Now, what is equilibrium? So equilibrium is going to be a point where the rate at which, where the rate at which the forward and the backward reaction are occurring at the same rate. Okay, so that would mean that the concentration of these is supposed to be kind of constant. Okay, so how can I best put this? What basically is going to happen is, of course, this may continue going straight and straight to indicate that the concentration of the reactants and products are the same. Now when it comes to the graph of the rate, you basically notice that they will be at the same rate like that. So if that is the graph, and then we're taking this to be our rate, and then this is our time. So you notice that the rate of one was higher, and then eventually they get to be the same. So the rate of the forward and the backward reaction is equal. That is what we call equilibrium. So chemical equilibrium occurs when the rate of the forward and the backward reaction is basically equal. So the rate at which A and B are reacting to give us C and D is equal to the rate at which C and D are reacting back to give us what? To give us A and B. So that is what we call chemical equilibrium. Now, as the system approaches chemical equilibrium, both the forward and the reverse reaction basically are occurring. Now at equilibrium, we've said the forward and the backward reaction are going to be the rate of the forward and the backward or the reverse reaction are proceeding at the same rate. And then one thing that you need to note as at chemical equilibrium as well is the amount of the reactant and products remain the same. So amount of reactants and products remain constant after equilibrium or at equilibrium. So later on we understand what basically happens is when a reaction has reached equilibrium, and then you basically get to add maybe more of externally, you get to introduce more of D. You increase the concentration of D or increase the concentration of A. What basically happens, there will be shift in the equilibrium. Okay, so I think that is a basic introduction to chemical equilibrium. Let's proceed and just basically get to talk about how to calculate the equilibrium constant. We've already established to say if you've got A and B reacting a chemical reaction to give you C and D. Now for a reversible reaction where you have also C and D reacting back to give you A and B, if the rate of the forward reaction is equal to the rate of the backward reaction, then the reaction is said to be at chemical equilibrium. Now there's one concept that I need to also mention. In a case where all the reactants and the products are in the same phase, let's say they are all in gaseous state, same state, equilibrium in this case is called or referred to as homogeneous. Homo means the same, so homogeneous equilibrium, same phase. Obviously you might guess what the opposite is. In a case where you may have a combination maybe of a solid there or even a liquid, okay, where all the products and the reactants are not in the same phase, that is referred to as heterogeneous equilibrium. Okay, just in case you get to meet that, so it's not complicated. Now we need to talk about the calculations of K. So K is referred to as the equilibrium constant. Okay, now considering the same reaction, taking stoichiometric coefficients to be their small letters, how do you express the equilibrium constant? So the equilibrium constant for gaseous reactants can actually be in two ways. You can have what we call Kc, you can also have what we call Kp. Now Kc is basically dependent on the concentrations, so the C denotes concentrations of the reactants and the products, and then the Kp is dependent on the partial pressures of what? On the partial pressures of the gaseous reactants and products. Okay, so that is because pressure of course is proportional to the concentration for gases in a closed system. So therefore the expressions are expected to be the same. So the basic idea is this. So the basic idea, yeah, sorry for that. So the basic idea is when you look at this, Kc is going to be expressed as follows. Kc will be equal to, now one thing that you need to understand is whether you're looking at Kc or Kp or any K, whether it's a reversible reaction as it is in this case for equilibrium, it is always going to be the product to be on the numerator and then the denominator to have the reactants. Alright, so what we expect in this case is for our products we have C and D. Now use these square brackets to denote that we're dealing with concentrations, and then we divide by the reactants. So we have A and B. Okay, so that is their products. Now we need to add or raise them their stoichiometric coefficients. So if you look at A and B, their stoichiometric coefficient, in this case we've used their small letters to denote that. So that would be A and B. Then for the products as well, C and D. So it's products divided by the reactants and then raised, of course, to a stoichiometric coefficient. That is the way you express your K. So all the same concept applies to the Kp. Now what will be different is we'll have the pressures of the reactants as well divided by the pressures of the reactants. Now of course even these are also supposed to be raised to a stoichiometric coefficients, right? So we expect to have C, D for the product, that is, and then A and B small letters 4. So you've seen the kind of brackets that I'm using to denote that that is not concentration, that is just pressure. Okay, so these brackets are specially used for concentration. So that is basically the way you can express their Kc and the Kp. Now one more important thing that is very important to note is when you have solids and liquids do not appear in the Kc or the Kp expression. In other terms, the reason is very simple. Solids and liquids are considered to be pure substances, so their concentrations will be taken to be 1. Okay, so that is very important. So adding a 1 or multiplying anything by 1 is as good as leaving it out. So that's why solids and liquids do not appear in the Kp or the equilibrium constant expressions. Okay, now let's look at a practical example where we've got an actual equation and just basically see how we can write the K expression. So we'll have a very simple equation like that. Gaseous state. So this is a single reactant reaction, single product. Okay, so I believe you expect that for the rate of the forward reaction, of course if you want you can split it up, but of course you're able to understand that this is your reactant in the forward reaction and that is your product in the forward reaction. So in terms of your K, we'll focus on the Kc. Your Kc is going to be dependent on the product, which is NO2. Now we said it's supposed to be raised to a stoichiometric coefficient, which in this case is a 2, so to be the power 2, and then divided by the reactant, which is N2O4, as well raised to the power 1, since there's only a 1 as a coefficient there. So that is the case for the forward reaction. Now as you might expect, in the reversible reaction, what do you expect in the reversible reaction? In the reversible reaction, if you are to write but let me just put it this way to avoid confusion and all. The Kc expression, whether you've got the reversible reaction as in this case, always take what is on the left as your reactants and then what is on the right as your product. So that is the Kc expression for such an equation. Okay, in a case where we can look at another equation where we've got nitrogen plus hydrogen in a reversible reaction. So I want you to feel free to pause the video and write the Kc expression and the Kp expression for this equation. Okay, so hoping you've attempted that, the basic Kc expression, where of course all these are gases, by the way, very important. So we said products over reactants. So products, we've got NH3, the power 2, and then we have, now why am I using that the power 2 is because it's the coefficient that we have there, and then for hydrogen will be raised to the power 3, for nitrogen just the power 1 because of their coefficients respectively. Okay, so assuming nitrogen was a solid, it wouldn't appear there or in short we'll just put like a 1, or as good as leaving it out in the K expression. Okay, so that is very important for you to understand that idea there. So in the next tutorial, let's proceed and look at how basically we can perform the calculations to using the ICE table, the use of the ICE table with dealing with calculations under chemical equilibrium. Okay, so for the Kp expression, of course, it's the same idea where we have the concentrations. We can just say the pressure of that, pressure of that, pressure of that. Of course, the brackets can be different as well. Okay, very important. So partial pressures only works when you're dealing with gases. Before we proceed and look at the Kc and Kp relationship, let's just try to look at a few questions to help us understand the use of what we are calling the ICE table. So the ICE table helps us to look at what we call initial, the change, and the equilibrium. So the basic idea of the ICE table is to help us determine the initial concentrations and also the concentrations at equilibrium. Okay, that is the idea. So the ICE table can also help us to find the value of Kc. Okay, so the letters I stand for initial, the change. So that is the initial, this is the change, and that is the equilibrium. So initial concentration, equilibrium concentration. I believe you understand what initial and equilibrium concentrations are. So initial, at the start of the reaction. Remember we said a reaction does not only start at equilibrium, it starts initially with only reactants, and then after some time, as products are being formed, they also begin to react with themselves to give us back what? The reactants. At that point where that begins, we call that equilibrium. So equilibrium will basically be at the point, actually not necessarily at the point where the backward reaction begins, but when the rate of the backward and the forward becomes equal. Okay, and then the constants remain the same, the concentration is maintained. So let's try to see the way we can use the ICE table to answer this question. So I've got 3 questions actually that we're going to look at. Okay, so to start, a closed system initially containing, so already the term is telling you initially, so initial. Now the equation, I need to take it note before we even get to, so we've got hydrogen, so that is the full equation. Hydrogen reacting with iodine, they are all in gaseous state. And then we have our product like that. So this is now where we'll write the ICE table like that. So for the initial concentration, let's take note of the given information. So a closed system containing 1 molar concentration of hydrogen. So we have 1 molar concentration of hydrogen, 2 molar concentration of iodine at 448 degrees Celsius is allowed to reach equilibrium. Now analysis of the equilibrium mixture shows that the concentration of HI is 1.87. So at equilibrium that is, the concentration of HI is 1.87. Just take note of the way I'm writing this information. So for your own information, the initial concentration of this product was a 0 because you initially started with only products, unless explicitly stated that there was an amount of it at start. But where a reaction is only starting with only reactants, the product is taken to be 0. Okay, any other piece of information that we're given? So calculate Kc at 448 degrees Celsius for the reaction taking place. Calculate Kc. So for your own information, it's very important to note that K calculations are only dependent on the equilibrium concentrations. We don't use initial concentrations. So for the initial concentrations or concentrations at any point in the reaction, is what we call Q. So Q denotes the constant at any point in the reaction. For the equilibrium constant K, it is only interested in the equilibrium concentrations. So in this case, we want to find Kc, so we're interested in the equilibrium concentrations. Okay, I hope that makes sense. So don't worry about Q. We'll talk about it later, where we'll look at the relationship between Q and K. You understand what Q is. But understand that K deals with equilibrium concentrations. The opposite is for Q. So therefore, in this case, we need to find the missing equilibrium concentrations for us to be able to find or calculate Kc. Now, for the change we use the stoichiometric coefficients, where for the products for the reactants, in this case hydrogen iodine, we have to put it as a negative, and then for the product as a positive. That indicates that as the reaction proceeds, you expect a reduction in the reactants concentrations and then an increase in the product's concentration. So we use a variable x to denote that. So we've got a 1 and a 1 for hydrogen and iodine, so put minus x. On the other side we put positive 2x. So I'm using the coefficients of the reactants and the products respectively, where I'm now including a negative for the reactants to indicate reduction. This is very important for the change, very important for you to understand what's going on here. Okay, so the basic idea is, for the equilibrium concentration, it's looking at how much you add initially compared to the change. So for the equilibrium, it will be 1 minus x, showing that there's a reduction in its concentration, as well as for iodine it will be 2 minus x. So I'm using the initial minus the change, or initial in other terms we only add, but because of the negatives it becomes subtraction. For the other part, if we are to express it, it's supposed to be 2x, or in other terms, let me begin with the initial. So it's supposed to be 0 plus 2x. That is for the equilibrium. Now, the good part about this one is the actual concentration has also been given, so we're able to find the value of x. So we'll say 0 plus 2x is supposed to be equal to the equilibrium concentration, which has been given to be 1.87. So we're able to determine the value of x, which will help us determine the equilibrium concentration of the other reactants, because we're using the value of x. So 1.87 divided by 2 will have a value of 0.935. Okay, we can substitute there to find the equilibrium concentration. So for hydrogen it will be 1 minus that, 1 minus 0.935, 2 minus 0.935. So for any information, at times they may give you the equilibrium concentration of the reactant. So if we are given, for example, a value here to say the equilibrium concentration of iodine was 0.2, you're also able to just say, okay, 2 minus the x should be equal to 0.2, so that you're able to find the value of x to help you or enable you to find the equilibrium concentrations of the missing parts, so that you're able to calculate Kc. So with that value of x, let's try to determine the values of the equilibrium concentrations. So 1 minus 0.935, so I can just substitute explicitly the value there. So the value obtained is 0.065, and then let's put a 2 as well. 2 minus that for iodine, 2 minus the value of x is giving us 1.065. So there we are. So we have the equilibrium concentrations of the reactants and the products. Now don't forget our formula for Kc. We said Kc, look at the products. The products will only have Hi raised to its stoichiometric coefficient divided by the reactants as well raised to the stoichiometric coefficients. Okay, let me indicate the stoichiometric coefficient. So for our product we have got a 2. Our reactants we only have 1s there, so no change. We can substitute for iodine, for H, I don't know how you pronounce that, hydrogen iodide, Hi, The equilibrium concentration for our product was 1.87 as given in the question explicitly to the power 2. And then what else? Hydrogen 0.065, and then iodine 1.065 raised to the power 1 and 1. So you can determine you can actually perform the calculation. So I'll start with the bottom. 1.065 raised to the power 1 multiplied by 0.065 raised to the power 1 as well, and then we need to divide that into what? Into 1.87 squared. 1.87 raised to the power 2. 1.87 raised to the power 2 divided by that. So the value that I'm obtaining here is 50.5. So that's a K. So remember, K has got no units. We're on the other part now. So in this question, the equation given is hydrogen. I think this is the same equation again. Okay, giving us 2H iodine, and then K has been given in this case. Now they want us to find the equilibrium concentration of HI, which is our product in this case. I don't know if it's hydrogen iodide. This part, we need to find this equilibrium concentration. Now in the question, what information have we been given? So draw up our ICE table. So try to fill in the ICE table and try to answer the question, applying the concepts we've learned from the previous question. Okay, so initially the concentrations have been given, so the term initially exists there. So for hydrogen it was 0.5, for iodide it was also 0.5, and then I also mentioned that unless stated, the product's concentration is 0 at start. For the change, look at the coefficients. So there we've got a 1, 1. Now I said you add a negative for the reactants to indicate reduction. For the products, positive, indicating an increase in the concentration. Now, have we been given any equilibrium concentration? Not at all. So 0.5 minus x, again there 0.5 minus x, there it will be 0 plus 2x, which is just as good as 2x. So the Kc expression is expected to be, for the products we only have iodide to the power 2. So I'll get its concentration directly, which is 2x raised to the power 2 over, and then 0.5 minus x, and then the other one as well, 0.5 minus x raised to the power what? They are all raised to the power 1. They are all raised to the power 1. Now the value of K has been given to be equal to 64. So that tells us that we've got the ability to find the value of x, which we then are going to use to help us substitute in the equilibrium expressions that we have, and they help us find the missing concentration that is required. Now if you look at the x that is on the bottom there, it's leading us to the point where we've got what? Where we have a quadratic function. But why are we not in this case? Most of the cases, the value of k are going to be less than 1. Actually, even less than 1 by 10 to the power negative 3. In such a case, you are just supposed to cancel that negative part, as you see in the practice questions that are coming later on. You should be able to cancel it out to avoid reaching a point where you have what? A complicated quadratic function. But in this case, since the value of k is way big, as big as 64, We just have to handle it as it is given. Okay, so you understand that this is matching up. So you actually have 2x squared, 2x to the power 2 divided by, so on the bottom as well we can take that as squared since there are 2, equal to 64. And then you can simplify your work by squaring on both sides. Square root, square root. Okay, so what do you expect at that point? So on the left, the square will just go away, so that we remain with 2x over 0.5 minus x is equal to, and then we have what? We have 8. So at that point I believe things are easy and simplified. If you do cross and multiply, you should be able to simplify that linear equation. So we have 2x being equal to 8 times 0.5 is a 4 minus 8x. Like terms, we have 10x is equal to 4, x is equal to 4 over 10. 4 over 10, that is like 2, 5, I believe 0.4. So after finding that, you're able to find the equilibrium concentration of what? Of your product, since that's what they are looking for. So the equilibrium expression is 2 times x, so 2 times 0.4, which will give us 0.8 molar concentration. Okay, so this is how you use the ICE tables. We just have a last question that I want you to try out, okay, as your practice question. So the following reaction is carried out in A. So the volume has been given there, the value of K has also been given. Now the question is asking us to find the mass. What is the mass in grams of a product? So we only have a single product, so you know the product they're talking about at equilibrium. If there is 40 grams of sulfur dioxide, the molar mass has been given for you, so that is grams per mole, and then 100 grams of water as well. So you know you're able to determine the molar mass of water, okay, as well. 2 times, what's the molar mass of hydrogen? 1.008 plus oxygen 15.998. Okay, so approximately value there is 8.002. So that is your also molar mass of water approximately. Now we've got the molar mass of both water and sulfur dioxide, so you know where this is going, right? Because you understand that for K we are dealing with concentrations and not masses. So if we are to find the mass of a product, we need first of all to find its what? We need first of all to find its concentration. We're able to do that, right? So come up with the ICE table. Come up with the ICE table. Now don't forget the equation. The equation has been given there for us. So SO2 plus water giving us that product H2SO3. So what were the initial concentrations? So we've not been given any initial concentration. So the following reaction is carried out in a 1 liter vessel. What is the mass of the product at equilibrium? If there is, so I believe these are now the initial concentration. If there is 40 grams, we're going to take that to be the initial concentration, or to be the equilibrium concentration from the way the question has been phrased. So anyway, the question tells us from the way it's coming out, I believe that is the equilibrium concentration. We'll take it as equilibrium concentration. So what is the mass of a product at equilibrium if there is? So I think that those masses have been given for equilibrium. So we have the ICE table. So we have been given the equilibrium concentrations, sulfur dioxide and the water. Now we've been given in terms of masses. So before we can actually have our ice table, we need to determine the actual concentrations. Now don't forget that is the molar mass of water, that's the molar mass of sulfur dioxide, or one given, one calculated. Let's find the number of moles. So number of moles, starting with sulfur dioxide, is supposed to be the mass. So the mass has been given to be 40 grams. So the mass 40 grams divided by the molar mass, grams per mole. And then number of moles of water. So for water, what information has been given? The mass is 100 grams. The molar mass we've calculated to be 18.02 grams per mole approximately. I'm just able to recall that. You can perform the actual calculations. I believe the answer will not be different. So 40 for the sulfur dioxide divided by 64.066. So we'll take up to 4 significant figures. 6243. Okay, we'll take up to 5. And then this one, 100 divided by 18.02, 5.5494. So we have the number of moles. Now number of moles, we have moles. Now the good part about this question is the volume has been given to be a liter. So you divide by 1 liter so that you have what? Molar concentration. So you know where that is going, right? So we have the concentrations. So that one becomes the concentration of what? Sulfur dioxide. The one on the bottom, that's for water. So this is for water. So I can bring back the ice table. So therefore the equilibrium concentrations as follows. For sulfur dioxide, the one on top, it will just be the same, 0.624, since we're dividing by 1, 0.62436 molar concentration. For water, it's 5.5494 molar concentration. Okay, what else do we need? What other piece of information do we have? So apart from K being given, there's nothing else. So K is equal to 0.115 there. Now the change, for the change we can say, we'll look at the coefficients. That's a 1, that's a 1, that's a 1. So we have minus x, and then here we have plus x. Now there, of course, we know we started with 0. The equilibrium, do we know anything? We don't know anything there. So there's nothing for the equilibrium here. And so for equilibrium, we can express it in terms of x. So 0 plus x, that is just going to give us x. Okay. Anything that we have as well? I believe we don't have anything. So now the question is asking us to find what is the mass of the product at equilibrium. So if we can find the concentration, it will be very easy for us to basically get to find what? To find the mass. Because if we've got the concentration, we're able to find the number of moles. The number of moles will help us to find the mass using the molar mass. So we know, one thing that we know is we're able to express our K in terms of these given values at equilibrium. So our K is basically 0.115. Now we expect that this is supposed to be equal to, for the product we only have a single value x, supposed to be raised to the stoichiometric coefficient, which is a 1, divided by the reactants equilibrium concentration, so 0.62436 raised to the power 1 as well, multiplied by 5.5494 raised to the power 1 as well. so we don't have squares here. So it seems for us to find the value of x, if we do cross and multiply, x will be equal to all these other three values would have to multiply against each other. Okay, so therefore we have 5.5494 multiplied by 0.62436 multiplied by 0.115. So the value of x is 0.39845. Now what is the concentration, molar concentration? Now don't forget that that value of x is exactly matching up with the equilibrium concentration of what? The product. Because we said 0 plus x was equal to x. So that becomes the value there. Now I want you to be very careful and be very attentive here. Now the volume in the question was given to be 1 liter. So under your stoichiometry, you know that concentration is basically the number of moles dissolved in a volume of a solution. So if you are to make number of moles a subject, it becomes a product of concentration and volume. So your concentration is that your volume is a liter. So if you multiply by 1, nothing will change. So therefore, in a case where the volume is equal to a single liter, the number of moles is the same, 0.39845 moles, because of a single liter. So number of moles is given as a product of concentration and volume. So we've got the number of moles now. Now, one thing that we know is, if we are to find the mass as required, and then if you have the number of moles, we also know that number of moles is given as mass over molar mass. So if you are to make mass a subject, mass also becomes a product of number of moles and molar mass. So we have our number of moles to be that value. So we need to multiply by the molar mass of our product. So you know what? You've got hydrogen. So go to your periodic table. 2 times 1.008 plus, for sulfur, I think the value should be 32, because just confirm it. Sulfur, you only have a single sulfur. Put its molar mass plus 3, multiply by 15.99, should be 8. For oxygen, times 3. So what you're going to get there is the molar mass. The molar mass of what? You're going to get the molar mass of. So let me just confirm the actual value for sulfur molar mass on the periodic table. So for sulfur, okay, yeah, I was right, 32. So 32 is the value there. So 32.0 something. So let's try to just, So these formulas, by the way, you don't need to memorize them. You can just use dimension analysis to be able to work around that. So for the molar mass, let's try to add 2 multiplied by 1.008 and then plus 32 plus 3 times, let's just say approximately 16 for oxygen. So the value is approximately 82.016 grams per mole. So the moles will be able to cancel out, so it just remains 2 grams. Now that value multiplied by the 82.016 multiplied by 0.39845. So the value that I'm getting is approximately 32.679 grams. Hopefully my calculations are okay there. So yeah. Now looking at the piece of information given just as a tip, our K value had 3 significant figures, this had 4, that had 3. So leaving our answer to 3 significant figures would cut it there, so it will be 32.7 grams. Okay, so let's proceed now and look at the relationship that is there between the Kp and the Kc. Okay, beginning with the formula itself. I'm sure you know this equation already. Kp is equal to Kc RT raised to the power delta n. So we want to prove how come that's true. So we're going to use this setup where we have a reaction A and B reacting to give us C and D. And then of course we are going to use small letters to denote our coefficients. So A, B, C, and D. Okay. So we know that from this equation, our Kp expression is going to be dependent on the pressures for what we have. So of course in this case we are assuming all these are in gaseous states, right? So pressure of A, and then we say pressure of so of course it's supposed to be products of the reactants, not so. So for products we have C. So I'll say the pressure of C, pressure of D, and then of course they're supposed to be raised to a coefficients C and D respectively. And then for the other one again, for our reactants we have pressure of A and then we have pressure of B. So I do know that you guys already understand where all these are coming from. This is the Kp expression in terms of pressure. Okay. So now we do know the ideal gas law. So the ideal gas law tells us to say that pressure multiplied by volume is basically equivalent to nRT, right? Very true. What happens if we decide to divide by volume on both ends? So dividing by volume, this is what we're going to have. So the pressure is going to be equal to nRT. So I'll try to isolate the V and divide it into what? The N there. So number of moles divided by the volume. What does it give us? So we basically know that that is going to be equivalent to what? To molarity or concentration, if you like. Okay, so this is the equation that we've come up from the ideal gas law. Pressure is equal to mRT. Okay. So now, this tells us to say that when you talk about the pressure of air, for example, using the same equation, if you say the pressure of air is going to be equal to the concentration of air, because M is denoting the molar concentration. So if we are talking about air, the pressure of air is going to be equal to the molar concentration of air multiplied by RT. And that is going to apply to everything that we have for all the pressures of the different letters that are being represented in this equation. And let's try to substitute that now in the next step. So I'll write Kp is equal to, so where is the pressure of C? It's going to be the concentration of C, RT, okay, raised to the power, that is C. And then of course I'll go to the pressure of D, which is going to be a concentration of D, RT, raised to the power D. Okay, so I can use, let me just use a different color so that we're able to see clearly. So that is C and then that is D. And then we can divide. So on the bottom we have the pressure of air. So it's going to be the concentration of air and then RT, and then that is also supposed to be raised to the power of what? The power of A. And then what else do we have? And then we have, of course, the other one is going to be raised to the power B. So the concentration of B, RT, is also raised to the power B. So this is all coming from the ideal gas law. Now let's try to simplify this and make sense out of it. So we need to distribute the powers, right? So I'll just do that from that same step. So we do know that if we are raising everything to the power C, what is in the brackets here? So I can drop the power C. It's going to be the power C, and then even this is going to be the power C, so that I can remove it outside there. So what it means is it's like if you have 2 times 4, and then this is raised to the power 2. It's the same as 2 to the power 2 times 4 to the power 2. So we are doing the same to what we have. So we're just going to distribute the powers. So D is going to be distributed to that concentration as well as RT to the power D, Even on the bottom, A is going to be the power A, and then RT is also going to be the power A. For B as well, to be the power B, and then RT is also going to be the power B, so that I can remove these ones that are outside. Okay. Now, hoping that you've understood this stage, what we can do is we can separate them. So we'll move to the next stage. Kp is going to be equal to, so what do we have? We have a concentration of C raised to the power C, and then we have RT raised to the power C, and then for the other part we have the concentration of D raised to the power D, and then we have RT raised to the power D. Okay. And then we can divide concentration of A raised to the power A, and then we have RT to the power A, and then of course the other part we can have concentration of B raised to the power B, and then we have RT raised to the power B. Okay, so I can now erase this part, the top part, so that we see what we're going to have. So now, Kp, we're trying to derive that Kp is equal to KCR to the power delta N. So what can we do? So I'll correct everything that is dealing with Kc. These are dealing with Kc. Since we know that multiplication is commutative, so it doesn't matter what you start with in your writing. So I'll start with a concentration of C, and then I'll go to the concentration of D. And then even on the bottom I'll do the same. I'll start with the concentration of A, and then the concentration of B. Okay, and then I can draw a line in advance here. Okay, and then of course we know these are supposed to be raised to where C, D, A, and B. From the equation that is on the bottom there, that's what we are saying. Now what remains is, so we have the product of RT and RT. So when you're multiplying the same bases, so RT and RT are the same. So from the rules of indices, when you're multiplying, what do you know there? So if you're multiplying the same bases, you just add the powers. So you have the addition of C, you have addition of C and D for the top part. And then on the bottom equal, you have RT multiplying by RT, which we're going to show, which is also going to be the addition of B and D. Oh, sorry, the addition of A and B. So we have A and B, right? So if we go back to our equation, our very simple equation, A reacting with B, giving us C and D, and then looking at the coefficients to be A, B, C, and D, what can we see? So if we are to write the Kc expression for this equation, what are we going to have? So it's basically going to be, of course, just this part that we are saying there, right? That is our Kc expression. So on the next step, we can say our Kp is equal to Kc. Now multiplied by what? So what happens if you are dividing the same bases? So RT is the same, so maintain it, and then we're going to have a difference between what? So the one that is on the numerator part is C plus D. We'll add that, and then we'll subtract the power for the denominator, which is A plus B. So now the addition of C and D, this is for products, A plus B is for the reactants. So instead of writing C plus D minus A plus B, we can just say it is just the change in the number of moles. So therefore, our Kp is equal to Kc RT raised to the power change in number of moles, which tells us to say C plus D are the stoichiometric coefficients of our products, A plus B are the stoichiometric coefficients of our reactants. So that is what the delta N represents. And this is a proof that we can have for this equation. So thank you very much for watching. We'll look at the relationship that is there between K and Gibbs free energy, and then we'll look at the few practice questions that I have with me there to just help us understand everything. Okay, so here is the other question. So what relationship is there between K and Gibbs free energy? So if you've already looked at Gibbs free energy from electrochemistry, I believe this should not be strange to you. So Gibbs free energy is you are calculating the standard one by being dependent on the standard cell potential. I believe you're able to remember. And then for the non-standard Gibbs free energy, we said the non-standard Gibbs free energy was dependent on the standard Gibbs free energy plus RT natural log of Q. So this formula comes from thermodynamics. Okay. Now, this equation, you can remember to say, after substituting in the value of the non-standard, which can be represented as negative of Faraday's constant, standard cell potential, and then again we do the same there, we put now the standard cell potential, and then if you try to make the non-standard cell potential to be the subject of the formula, this is where you come up with what we call the Nernst equation, which is very useful under electrochemistry. But now in this case, that's not our interest. In this case, we want to show the relationship that is there between K and Gibbs free energy, meaning that Gibbs free energy should still stand in the formula. Okay. Now, it's very important, and this is actually very important even under electrochemistry. Okay, so you may be watching this video under chemical equilibrium. You may also be watching this video under electrochemistry. Okay, so the relationship that is there between K and Gibbs free energy is as follows. So we know that at equilibrium, very important, at equilibrium you should know that the non-standard Gibbs free energy is equal to 0. Okay, that's very important for you to know. And then you should know that the value of Q, or let me just say K, becomes Q. So the difference between Q and K is as follows. The value of K is the reaction constant at equilibrium. Q itself is at any point in the reaction. So what that means is, if you have the reaction, I believe I'm talking to somebody who has already looked at all this. You've looked at chemical equilibrium already, so I hope you've already looked at chemical equilibrium. So we understand that when you're looking at an equation like this one that I've written below here, you should be able to find the Q or the K. The basic idea is it's going to be the products that you have raised, of course, to the stoichiometric coefficients divided by the reactants. They should also be raised to their stoichiometric coefficients. Now what I'm trying to say is you can calculate the value of Q at any point. Now K is a special value of Q which occurs at equilibrium. Or in short, what I'm trying to say is K is what we call Q at equilibrium. So Q becomes K at equilibrium. So calculations are the same. Now if you are just starting, for example, initial concentrations, remember K is calculated using the equilibrium concentrations from the ice table and all. But if you are looking at concentrations of the reactants at any point, the value calculated is called Q. Hopefully you now understand the difference between Q and K. Okay, so at equilibrium we're going to call our Q our K so that we don't get confused. So substituting what we have in this equation, so on the left where we've got non-standard Gibbs free energy, non-standard Gibbs free energy, 0 is going to be equal to the standard Gibbs free energy plus RT. We'll call now our Q as our K. So we can make the standard Gibbs free energy to be a subject of the formula. So this part can go the other side. So our standard Gibbs free energy becomes negative RT natural log of K. I don't think there is any issue there with what I've done. Okay. So I took this on the other side and then I just exchanged them. So this equation is one of the equations that's very important, that will enable you to calculate the value of K in a case where we've given you the standard Gibbs free energy and the temperature. Okay, very important. Now from there, We also need to find the relationship that is there between now the non-standard Gibbs free energy and the value of K. Okay, so taking this to be our standard Gibbs free energy, we can substitute in the original equation that we came up with, which comes from thermodynamics. We can substitute the value of the standard Gibbs free energy. So you notice that the equation will become very similar. This is going to be negative RT natural log of K plus RT natural log of Q. So you can factorize a common part there. So a common part is RT. What else? RT is a common part. And then I'll start with a positive part. So if we remove RT there, we remain with natural log of Q. And then minus natural log of K. So you know what logs tell us. So logs tells us that if you've got the same bases there, all you just do is factor out the log and then divide. So Q over K. So that relationship is very important as well. That formula is also very, very important when you're looking at the relationship between the non-standard Gibbs free energy and Q and K. So these two equations are very important under the study of this topic. Okay. Now let's look at the practice questions to just help us understand how we can basically get to use these equations to help us determine the values. Okay, so the first one is asking us to calculate the value of K for the reaction of nitrogen oxide and oxygen to give nitrogen dioxide at 25 degrees Celsius. So for this reaction, the standard Gibbs free energy has been given to be that. Okay, so what are we supposed to do? So we've already established to say the relationship between the standard Gibbs free energy and the value of K is negative RT natural log of K. So the Gibbs free energy has been given to be negative 70.5 kilojoules per mole, and then negative, our value of R is 8.31. That's a constant that you shouldn't worry about. So it's joules per watt, joule per Kelvin. And then what else do we have? Then we need the temperature. The temperature is supposed to be in Kelvin because you can see the value of our R is also in kelvins. So if we do substitute 25, so if we're converting to Kelvin, I believe we're supposed to add a value of 273, if I'm not mistaken. So 273 plus 25 gives us 298. So we have 298 kelvins, and then we also need to now put the natural log of K. Now you can also pay attention to say there you have kilojoules, here you just have joules. So it's good, it could be a good idea if we can actually bring back the kilo. Kilo means times 10 to the power 3. So that's why indicating the units when you're solving is also very important. Okay, so kilojoules now per mole. So we're trying to collect the like terms. Here we can't collect the like term. This is multiplication. So let's try to multiply what we're going to have. So after multiplying, of course, we expect the kelvins to cancel out. And then we're multiplying the 298 multiplied by the 8.314. So the value is negative 2477.572 joules, and then you have natural log of K. So we can divide both sides by this value. So in this side it's going to go away, and then you divide it this other side, negative 2477.572 joules. So the joules as well will cancel out. Okay. So what do we expect now at that point? So let's try to divide what we have. So we have negative, on top here we have negative 70 multiply by 10 to the power 3, and then we need to now to divide. Okay, divide by what? Divide by 2477 and all. So at this point I have my natural log of k, which is on the left, being equal to, so don't forget I'm dividing a negative value and the negative value, so meaning that the value will be positive. So natural log of k is equal to 28.25346. So to find the value of k, we understand that the base from the natural log is e. It can go the other side, so that our k will be e to the power 28.25346. So what value of k should we be expecting? So I'm on my calculator, so e raised that power. The value seems to be a bit big. So the value I'm getting is 1,863,481,275,337.2. I think that's like a billion. So we need to round it off. Unfortunately, the calculator that I'm using right now, I can't take to standard form. But anyway, we'll still calculate. Let's try to count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12. We've moved 12 times. So that becomes 1.9 because of the 6 there times 10 to the power 12. That's the value of our k in this case. We can move on and look at the the other question. Okay, so this also looks very interesting. Now here let's look at the piece of information we've been given. So take note of the equation. So the equation we've been given is nitrogen plus oxygen gives us 2, like that. Okay, so I actually needed to mention to say in this case we needed to write the chemical equation as well, so that the number of moles was not necessary, because we can see that if the mole of oxygen, so if you write the equation, which is this one, you notice that the number of moles of oxygen in this reaction is just a single mole. So meaning that we just needed to say, okay, since we have a single mole of oxygen reacting, we forget about this. This is the Gibbs free energy that we have. Okay, I hope that clears things out. Okay, so in this case now they want us to calculate the non-standard Gibbs free energy. I think this is where you got to be careful now. They want us to calculate the non-standard. So you've already seen that for the standard. So the standard is dependent on what? The standard is dependent on the negative RT natural log of k. Now for the non-standard, this is where now you combine the original equation. So this is why we said now the non-standard Gibbs free energy is equal to what? RT natural log of Q over K. Yes. So for us to find the non-standard Gibbs free energy, we need to have the value of Q and K. The value of T, which is the temperature, has been given already to be 428 kelvins. The value of R is known as a constant, 8.314. So we just need to find Q and K. Where are we going to find them, or where are we going to get them? Now For value of K, we know that we can use the basic relationship between the standard Gibbs free energy, which is equal to negative RT natural log of K. So let me go in this way directly to just make natural log of K the subject. So we divide both sides by negative RT, so our natural log of K becomes equal to negative standard Gibbs free energy over RT. What else? So our K becomes, we have got the base of E there, so it can just be E, and then you have negative. So anyway, whatever you have on the right should become the power of E. So for now, let's substitute from that point. So what do we have as our Gibbs free energy? Our Gibbs free energy there is 22.7 kilojoules. So we have 22.7 times 10 to the power 3, and then on the bottom our value of ER is 8.314, and then our value of temperature is 423. Okay, so that can be plugged in. So 22.7 times 10 to the power 3, which is as good as multiplying by 1000, and then divided by 8.314 multiplied by 423. Okay, so the value that I'm getting is approximately, after dividing, the natural log of K is equal to, the value is 6.454 something there, 69. This is a 6. So E raised to that. So E, the answer or the value of K I'm getting or I'm obtaining is 635.677. Okay, now the other thing that we need is to find the value of Q. How do we find the value of Q? So the value of Q, now noticing the question actually under the conditions. So for the non-standard, this is the non-standard Gibbs free energy, which is determined at non-standard. Okay, so at that point what you might expect is that your temperature has been given to be non-standard, of course, 423, and then these are the concentrations. So if these were the concentrations at equilibrium, it was going to be stated explicitly, or the temperature would entail where they tell you that temperature is equal to 298 kelvins or 25 degrees Celsius. But in this case, we want to determine the value of the non-standard Gibbs free energy with the given conditions, which are non-standard. So these concentrations have been given, meaning that we're able to find the value of Q by looking at the equation there. So our Q, just as we would calculate K at equilibrium, we'll look at the products. We only have NO raised to the power 2 as this stoichiometric coefficient divided by the reactants raised to the stoichiometric coefficients of 1. So for NO, which is a product, that is the concentration 0.01 the power 2 divided by nitrogen, it's 1 times 10 to the power negative 4, 1 times 10 to the power negative 4, and then multiply by 0.2 for oxygen. Okay, so feel free to grab your calculator there and just try to make calculations. So 1 times 10 the power, I'm beginning with the denominator, I know why, the power negative what? The power negative 4, and then multiply that by 0.2, and then divide that. So we need to divide the 0.01 squared, and then we divide that. So here the value of Q is accurately determined to be 5. So Q is equal to 5. So we have the value of K and Q. We are ready now to substitute in the equation. Okay, so there was an error in our calculation. So actually at this point, the value is supposed to be, because of this negative, when we divide 22.7 times 10 to the power 3 by 8.314 times 423, the value is supposed to be negative 6.45. So I can remove this part. Negative 4, 5, 4, 6, 9, 1, 1, 9, 5, 6. So at that point now, our value of K is equal to 0.001573, okay, 125. So I believe at this point the value of Q has already been calculated. So the value of Q that has been calculated is equal to 5. Okay, we can now go back to our formula and just try to substitute and see what we're going to get. So our non-standard Gibbs free energy is equal to, our value of R is 8.314, our temperature is 423, and then we have natural log of our Q is 5, our K is 0.001573, and so on. Okay, so with this value that we have, let's have 5 being divided by what we've obtained. So, and then after we find that, I'm getting something like what, 3000? Yes, after dividing what is in the brackets, I'm getting like 3178.38, and then we need to find the natural log of that. So that is for this part. So after dividing, we need to find the natural log. So natural log of 3178.386996. So the value I'm getting is something like 8. So that's like 8.064. Now we need to multiply that by 423, which is our temperature, multiply by the constant R, which is 8.314. So the value that I'm getting now for this non-standard Gibbs free energy is 28360.1. So if we had to take this in 2 kilojoules, the decimal point would have to move 3 times, 1, 2, 3, giving us 28.4 kilojoules. Okay, so at this point you can see now that the value of the standard Gibbs free energy is positive. Okay, now the last part, which says in which direction will the reaction proceed to reach equilibrium. Now that's the part that is focusing on the issue of Q and K. So we understand that the value of Q is also dependent on the product raised to the stoichiometric coefficient divided by the reactants raised to the stoichiometric coefficients. So in this case, if we try to see what is happening, we can see that if you compare Q, K is clearly less than Q, so Q is bigger. So if we are to establish equilibrium, only Q can change, so we can only change the value of Q. So the value of Q, which is dependent on the products, on the products divided by the reactants, if we are to reduce it so that it becomes equal to our K, we can reduce it by increasing what? The concentration on the bottom, which are representing the reactants. So that means that the reaction will favor the backward or the left, meaning more of the reactants will be produced, reducing the value of Q until it becomes equal to K at equilibrium. Okay, so each time they want you to determine the direction, just compare the value of Q and K. Are you enjoying this video lesson? So you can actually access the entire topic you are watching or the entire practice questions of a video that you may be watching right now. So if you go to our website is transcendedinstitute.net. Okay, so there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. So alternatively, you can access the videos using our learning portal. The link is learn.transcendedinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you like learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets, which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course, this applies to all these other topics that are available. Trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So if you open chemistry, these are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the tutorial sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally, biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel. Have you ever wondered what would happen to a reaction where we have reactant, let's say A and B, the reaction at equilibrium, and then we decide to do some changes? Let's say we decide to increase the concentration of our reactants, okay, A and B. What happens if we decide to increase the concentration of any of the two? Or what would happen if we decide to increase the concentration of the products? So what is our concentration? We increase the concentration. So what is the effect? What if we decide to reduce the concentration? Or what if we decide to increase the pressure of these gases, assuming these reactants are gases, or even the products as gases? What happens if we decide to increase the pressure? What happens if we decide to increase the temperature? What happens if we decide to increase the volume? Or what would happen if we decide to reduce the pressure, or reduce the temperature, or reduce the volume? So all these have got different effects. The temperature, increasing the temperature basically doesn't have a single effect. It depends on the kind of a reaction. Is it an exothermic reaction, an endothermic reaction? So all these changes basically refers to Richard-Taylor's principle. Richard-Taylor's principle basically summarizes what happens to a reaction at chemical equilibrium when these changes are done. So there's going to be a shift in equilibrium to just overcome the stress. So that is what Richard-Taylor's principle is all about. So we can summarize it to say, according to Richard-Taylor's principle, a system that is at equilibrium, when exposed or subjected to a disturbance, or we can say a stress, is going to shift in a way that is going to, we can use the word counter, or overcome the disturbance, or relieve the stress, okay, and re-establish the equilibrium. So it always wants to go back to equilibrium. Okay, so that is what is very important. So we need to understand the effects of all these things that I mentioned. Increase in concentration of either the reactants or the products, decrease or increase in volume, decrease or increase in temperature for the different kinds of reactions that we would have. Okay, so we now know what Chatelier's principle is all about. So let's get to work and then see what's the summary. Okay, so now what happens if we get to increase the concentration of, let's say, A or both? So increasing the concentration of A basically is going to favor the forward reaction. Okay, why? Because we're going to have more reactants. And of course, if you go back to your kinetics, you're very much aware that an increase in concentration leads to an increase in the rate of the reaction. Now, in this case where we have both the forward and the backward reaction, increasing the concentration of A would imply that we've increased the concentration of the reactants forward for the forward reaction. So whenever you increase the concentration, so if you increase the concentration of what is on the left, it will go towards the right. If you increase the concentration of what is on the left, it will go towards what? The left. That is the way it works. Okay. Now, the basic idea is you know that your K, or let's say your Kc, in case of concentration, is basically dependent on your products, which are C, the concentration of C, concentration of D, divided by the concentration of A, divided by the concentration of B. Of course, these are supposed to be raised to their stoichiometric powers. In this case, let's assume they all just have ones as coefficients. Excuse me. Okay, so what happens? Let's consider the case where we've increased the concentration of A. We increase the concentration of A. What happens? So if we increase the concentration of A, since the reaction is no longer going to be at equilibrium because we've altered or done something to the equilibrium, we've changed the concentration, so it will no longer be at equilibrium. So our calculation will be referred to as what? Q. Now, what is the meaning of that if we increase the concentration of A? Now, the fact that A is on the bottom as a reactant, if we increase it, it implies that we are reducing the value of Q. So in this case, it would mean that Q is now less than K. So we need to make sure again we somehow increase Q so that it becomes equal to K, because at equilibrium Q is equal to K. Q is just a quotient when you're not at equilibrium, and then K is at equilibrium. So knowing that Q is less than K, what is supposed to happen? So to make sure things become ordered, what is going to happen is after we've increased the concentration of A, which is on the bottom, and then it has reduced the value of Q, it's going to favor a forward reaction. And what happens if we favor a forward reaction? It would imply that our reactants now, our products, are now going to be increased, which is going to lead to an increase in the value of Q, and eventually Q will be equal to K, and then the reaction will go back to equilibrium. So that's the basic idea. Now, what happens in a case where we decide to do the opposite, where we decide to reduce the value of the reactants? Let's say A itself. So if we reduce the concentration of A, it would mean that we're increasing the value of Q, meaning that this time around Q is going to be greater than K. So we need to reduce Q. And how are we going to reduce Q? We'll reduce Q by favoring the backward reaction. So since we've reduced the concentration of A, it means that we need more of A. So it's going to now favor what? The backward reaction. And that would increase now the concentration of A so that we can now reduce the value of Q. Okay, so that is basic mathematics, and that's basically what happens, and that's the effect of the concentrations. So just know that if you increase something on one end, it is going to go the other side. If you reduce something on one end, that is where it is going to go. So we've said in a case where you decide to reduce A, the reaction will make sure that we produce more of A. If we decide to increase A, the reaction will need to produce more of the products. So that is what the Chatelier's principle summarizes. So we've talked about the concentration. What about the effect of volume and pressure? So we do know that when you're talking about gases, equivalent number of moles of gases at the same temperature and pressure occupy the same what? Occupy the same volume. What it implies is whether you have a mole of, let's say, oxygen, and also a mole of, let's say, hydrogen gas. These are going to occupy the same volume, okay? And of course, the value, if I'm not mistaken, at room temperature and pressure should be something like 24 decimeter cubed. Yeah, so that's what we know. So what does that mean? So what it means is, if we decide to, let's put it to that side, so that we have 3 moles of our reactants, of our products, and then this side we have 2 moles of our reactants, because a single mole there and a single mole. Okay. Now what happens if we decide to increase the volume of our system where this reaction is occurring? If we decide to increase the volume, what happens? So if we increase the volume, what it means is that we have more room now. More room for what? More room for the gases. Now in this case, which side needs more volume? So if you check this side, where we have got 3 moles, this one needs a higher what? A higher volume. Where we have 2 moles, it needs less volume. Okay. So if you increase the volume, it implies that you're going to favor what? The forward reaction, so that it's able to occupy and fill more of what? The space. So an increase in volume will favor the side with greater number of moles. Now on the other hand, if we decide to reduce the volume, it's going to favor the side where we have what? Where we have less moles. So in this case, it would be the backward reaction. So the number of moles basically helps us to understand that. And this is somewhat related to the next part, which is pressure. Now, what happens if we decide to increase the pressure? Try to think about it. So I'm pretty much aware that you guys already know what the relationship between pressure and volume. Not so. We know the relationship between pressure and volume. So these are inversely proportional to each other. And what basically that tells us to say is, if you increase the pressure, it implies that you're reducing what? Reducing the volume. So if you're reducing the volume, it means it's taking us back to what we're talking about, which would mean that it's still going to favor what? It's still going to favor the side which has got less moles. Okay, so that is the way it works. If you increase the pressure, you reduce the volume, so it will favor less moles. What happens again if you decide to reduce the pressure? If you decide to reduce the pressure, the volume is going to be higher, and in that case, we're going to favor a side with greater number of moles. So that's the basic concept that you need to understand about pressure and volume. Very, very simple. Just know that the higher the volume, it will favor the side with greater number of moles. Okay, let's try to move now and talk about the most interesting of all, according to me. That is temperature. Because temperature depends on the kind of reaction that you're talking about. Is the reaction endothermic or exothermic? So that explains what is all going to be, what's going to happen. Now, we use the same example of ours. Okay. And then let's say we have C and D. Okay. So now what basically happens in this case? Let's say this is an let's say endothermic reaction. So what is an endothermic reaction? So an endothermic reaction is basically a reaction where we know to say a reaction is going to be gaining what? It's going to be gaining it according to thermodynamics. So gain of it is an endothermic reaction. So in some questions, you may find that they've written to say on the reactant side they put, let's say, plus 10 joules. That would imply this reaction needs to gain a bit of energy for it to progress. Okay. Now the opposite is true. When you see energy being added on the other side in joules, it implies that there is loss, okay, or production of energy. Okay, so that's what you need to know. In some cases, they may give you what we call a thermodynamical equation, where they'll just write the energy towards the end, and then they'll show a sign. Let's say plus 10 joules. That would imply it's what? It's still endothermic. Now, if I put a negative, it's exothermic. So the sign tells you whether it's exothermic or endothermic. Of course, it may be in kilojoules. Okay. Now, what happens if we decide to increase the temperature of the reaction that is at chemical equilibrium? We decide to increase the temperature, and then this is an endothermic reaction. So think of it in the way I've talked about it, where we say in an endothermic reaction, we need to add it as what? as a reactant because it's somehow being added. Okay. So in an endothermic reaction, we show it as a reactant because it's gained. So if we decide to increase the energy, that would imply that it's somehow more like we are increasing the concentration of the reactant. So in such a case, this is going to favor what? The forward reaction. Okay. And then in a case where you decide to do the opposite, you decide to reduce the energy being added by being the temperature. If you decide to reduce the temperature, what happens if you decide to reduce the temperature? So if you reduce the temperature, the effect is going to be the energy is not going to be enough. So we need to reverse the reaction because we know if a forward reaction is endothermic, it implies that the backward reaction is going to be exothermic. Okay? So this 10 joules is being added in the forward reaction. It's acting as a reactant. Now in the backward reaction it's going to be produced. So if we reduce the energy that is being gained, it would imply that we would need this reaction to favor what? The backward reaction, so that the energy can be reproduced and be enough for the reaction of a forward reaction. Okay, so that's what you need to understand. And of course, this is not very difficult to understand as we even switch on to an exothermic reaction. So if we change to exothermic reaction, that would imply that we need to put the energy on our right hand side so that we think of it as a product of the forward reaction. And in such a case, if you decide to increase the temperature, if you increase the temperature, so equally, it's more like you are increasing the product's concentration. So this would favor the backward reaction. And of course, if you decide to reduce it, what is that? It's more like you're reducing now the product's concentration. So it's going to favor what? The forward reaction. So these are very, very simple concepts that you need to understand under the Chatter's principle and shifting equilibria. So we've already covered the introduction to Chatter's principle or shifting equilibria. Now in this video we're just going to go over practice questions on the same. So and our first question says we need to define what Chatter's principle is. So the basic idea behind Chatter's principle is that when you have a reaction at chemical equilibrium, when you apply a change, the reaction is going to act in a way that it tries to reverse the change so that it goes back to the equilibrium point. So the basic idea is if you have A plus B as a reactants, and then let's say all these are gases at equilibrium, and then you decide to increase the concentration of A. So you've increased the concentration of A, but the reaction itself wants to go back to its initial point. So once this reaction is going to act in a way that the concentration of A reduces, and the concentration of A can only reduce if we decide to do what? If we decide to go the forward way. So meaning that more of C is going to be produced. That is what the Chatter's principle tells us. So a reaction at chemical equilibrium exposed to a stress or a disturbance will act in a way that it relieves the stress. Okay, that's what it's all about. So that is because of dynamic equilibrium. Okay, so it changes so that it goes back to its original point. Now, what is meant by a stress? What are some of the ways an equilibrium can be stressed? So a stress is a change. So what are some of the ways an equilibrium can be stressed? So by adding concentration of the reactants of the products, by increasing the temperature or reducing the temperature, by increasing the pressure or reducing the pressure, by increasing the volume or reducing the volume. All these are different kinds of stresses that we can basically stress an equilibrium. So going to the third question, which says given this equilibrium, predict the direction of shift for each stress. Okay, so in the previous video we covered the effects of all these kinds of stresses. Now if you look at the case that we have, so the first one says decreased temperature. So when you reduce the temperature, you need to understand, is the reaction exothermic or endothermic? Now the idea that we have energy being added on the reactant side implies that this is an endothermic reaction. There's gain of it in this reaction. Okay, So it being written in form of the reactant makes it even easier. So if we reduce it, we need to, the reaction is going to act in a way that we increase the energy. So the only way that we can increase it is by going back, the backward reaction, because in the backward reaction it is going to act as though it's an exothermic reaction, so energy is going to be produced. Okay, now in the case where we get to increase pressure, what happens if we increase the pressure? So we said increasing pressure is going to reduce the volume. Increasing pressure is going to reduce the volume because these guys are inversely proportional. So when we reduce the volume, we say it's going to favor the side with less number of moles. Now in this case, there's one more, and then there are two moles on the right hand side. So what do you expect to have? Is it going to favor the reactant side? Is it going to favor the product side? What do you think? What is supposed to be the case? Okay, so in this case what we'll say is nothing is going to change because we've got equivalent number of moles. So in the actual sense, it's supposed to favor a side with less number of moles. Let's say if we had 3 moles on the left, it was going to favor the what? The backward reaction because we have less moles. Okay. And then if we go to see removal of HI, so that is a reduction in the concentration of what? Of our product in the forward reaction. So if we reduce it, reducing the concentration is going to favor the forward reaction so that we can reproduce it, because what we are saying is a reaction is acting in a way to relieve the stress that has been applied to the equilibrium. Now moving on to question 4. Question 4 says, given this equilibrium, predict the direction of shift for each stress. The first stress is the increase in temperature. So increasing in temperature, you need to understand, is it an exothermic or endothermic reaction? Now if you look at this reaction, you can clearly see that our energy is on the product side. So is it an exothermic reaction or an endothermic reaction? So the production of energy indicates that it's an exothermic reaction. So it being an exothermic reaction, this energy is more like a product. So if we increase the temperature, it implies we've increased a product. We're assuming we've increased the product. So that would reverse what? This would make this to go backwardly so that we can reduce the energy. Okay. So this is what you're supposed to do. And then what happens if you get to add the hydrogen gas? So adding hydrogen gas would imply that we are increasing the concentration of what? Of hydrogen. So the reaction is supposed to act in a way that we reduce the concentration of hydrogen. And that can only happen if we favor what? The forward reaction. Because in the forward reaction, hydrogen is going to react, so it will reduce. Decreasing pressure. What happens in a case where we decide to decrease the pressure? So decreasing the pressure implies that we've increased the volume, more room for our reactants and our products. So in such a case, when we increase the volume, we're going to favor a side with greater number of moles. Now in this case, how many moles do we have? So on the left we have 2. So the pressure again, it would not have any effect because we have got equivalent number of moles. So note that the pressure and volume only have an effect if we've got different number of what? If we've got different number of moles on different sides. That's a very, very important concept that we need to understand. Okay. So let's move on. We are now on question 5. Okay. So what is question 5 saying? Let me do this. So question 5 says, removal of that, removal of this, which is the product. So if we remove it, the reaction is supposed to reproduce it. So it's going to be only produced if we favor the forward reaction, because that is where it's the product. Addition of oxygen, that implies we're increasing the reactant, so it will still be forward reaction, so that they can be reduced. Decreasing the temperature. If you decrease the temperature, is it an exothermic or endothermic reaction? So this is an exothermic reaction because it's production of energy. So when you decrease the temperature, what does that mean? It's like you're trying to reduce the amount of energy being produced. Not so. So this is going to favor which side? So this one is going to favor forward reaction as well, so that there is more of energy produced because the temperature has been reduced. And then question 6 says, given this equilibrium, predict the direction of shift for each stress listed. So you can try out this one and see what you're going to get. So of course, addition of this implies we're increasing the concentration, so it's going to favor a backward reaction. Increasing pressure means we're reducing the volume, so we're going to favor a side with less number of moles because we have less volume. So this is still one more, so we still have equivalent number of moles, no change. Addition of a catalyst. What is the effect of a catalyst on the equilibrium? What does it do? Okay, what does it do whenever you think of a catalyst being added? So try to research on that. And then question 7, the synthesis of NH3 uses this chemical reaction. Identify 3 stresses that can be imposed on the equilibrium to maximize the amount of NH3 being produced. Okay, so what do you think? So we want to maximize the amount of ammonia being produced. What are some of the things that we should do? So we do know that for us to favor a forward reaction, that is when we are going to maximize the amount of ammonia. So what are some of the things that we can do? So I can decide to say, okay, since this is okay, even before we go to the temperature, the idea of just increasing the concentration of nitrogen will also increase the production. So we can also say increase the concentration of hydrogen. So we can just summarize that to say increasing concentration of the reactants, nitrogen and hydrogen. That's the first thing that we can do. In terms of temperature, looking at what we have, what kind of a reaction is this? So this is an exothermic reaction because there's energy being produced on the right hand side, as we can see. So what do we expect? So increasing the temperature, if you increase the temperature, what's going to happen? It's like you're increasing the product, so it's going to go backwards. So we can't do that in this case. So what we're going to do is we need to reduce the temperature. If we reduce the temperature, it implies we're reducing the energy. So the reaction is going to act in a way that more energy is produced. So we need to reduce the temperature. We need to increase the concentration of nitrogen and hydrogen. That is the way in which we are going to increase or maximize the amount of ammonia being produced in this reaction. Okay, what else can we do? Think of pressure. So in this case, we've got the number of moles that we have are different. So this on the we have 4 moles, and then we have 2 moles. So where we want the production of this guy. So we need a less volume. What can we do? So we'll reduce the volume, or we can say increasing pressure, because if we increase the pressure, there's going to be a less volume, which is going to favor a side with less number of moles, which is the ammonia itself. So those are some of the stresses that you can apply to that equilibrium to just maximize the amount of ammonia being produced. And of course, the last question also focuses on the same concept. And what do you think? Identify the 3 stresses that can be imposed on the equilibrium. And then if you look at this kind of a question, it's basically one and the same. Why do I say it's one and the same? I say it's one and the same because from what I'm able to see, I can clearly see that if you look at what we have, it's basically also an exothermic reaction. Yeah. So it's very easy to deal with. Suppose the reaction has the equilibrium constant K is equal to 1.3 by 10 to the power 8. What does the magnitude of this constant tell you about the relative concentrations of products and reactants that will be present once equilibrium is reached? Is this reaction likely to be a good source of the products? Okay, so basically, before we get to answer the question, we need to understand basically where the constant K comes from. Okay. So, your equilibrium expression basically
your Kc is basically dependent on the products of what? The reactants, basically the products of the reaction. That is, if you have a reaction, for example, involving your reactants, let's say your A and your B. Okay. So this should be a reversible reaction. So basically what you need to understand is you're going to have your products being part of that, the numerator on your K expression. Okay. Over what? The multiplication of what? The reactants A and B. Then these should be raised to their stoichiometric powers. So that's why I was putting the subscripts here. So A, B, and D, and C. So basically, that's what we're trying to say. So now, what are we trying to say? Now look at this. So now, when your K is about 1.3 by 10 to the power 8, what does it mean? It means that this reaction is favoring more of what? Because if you look at your Kc, it's like the higher the Kc there, the higher the Kc, the higher the top part there. So it's like your reaction is favoring more of what? You have got higher concentration of the products. That's the interpretation there. You have a very high concentration of what? The products as compared to the reactants. So basically, explaining what this means, getting back to our question which says, what does the magnitude of this constant tell you about the concentrations? I would say that since we know that when the products and the reactants are equal, when the products and the reactants concentrations are equal, that would mean that our Kc was going to be what? Our Kc was going to be 1. But in this case, since the value of K is very big, it tells us that we have more of what? We have more of the products. Okay. So it's actually about 30 million of that times of products as compared to the reactants. Okay. So reactants are very negligible. That's why we have a very bigger value of what? Of K. I've shown from the equation. So this reaction is a very, very good source of what? Our products. Basically, it's favoring more of the products as compared to the reversible reaction. Question 2. Write the equilibrium expression K for each of the following gas phase reactions. Okay, so some of these the states are not indicated, but all basically we need to understand is in this case basically all these are in gaseous. So we need to write our equilibrium expressions. So our equilibrium expressions basically are dependent on the products of what? The products. So in this case we have that as our only products. I'll write it. So the parentheses indicate that you're dealing with concentration. So then on the reactants I have nitrogen and oxygen. So these are supposed to be raised to the stoichiometric powers. So the nitrogen oxide on the right hand side has got a coefficient of 2. Then on the left they're just single, so just the 1 and the 1. So what we've written there is our equilibrium expression for the first reaction. Then for the second reaction, what do we need to expect there? Our K is basically going to be, so we have nitrogen dioxide on the right hand side to the power 2 divided by our nitrogen gas and what? And our oxygen gas. Okay, that's what we have. Okay, so we have our oxygen gas. That's what we have in this case. Is there any question there? Of course not. So now, going back to the last one, our K expression is basically also going to be dependent on what? On the multiplication of the products. In this case, it's a different case because we actually even have 2 products, so it will even make more sense here. So the key thing is you need to make sure that your reactants and your products basically are raised to what? To the stoichiometric powers. That's very, very important to note. So I'll start with my reactants. So for my reactants, that one just is a 1. Chlorine is a 2. Your hydrogen is a 2. And a 1 there. So this is our K, or equilibrium expression, for the gas phase reactions that we're given. Third question. At a given temperature, K is basically equivalent to 1.3 by 10 to the power negative 2 for the reaction that. So our reaction is between nitrogen. So we have that equation there. So we have nitrogen reacting with your hydrogen to give us what? To give us that. So now, we are now given the other reactions in relation to the same one that is above, so that we get to find the value K there. So what basically requires us to understand how the coefficients and also reversible reactions gets to differ in terms of a constant K. So now, this being our equation, which I've copied down there, let's try to come up with our K expression. So we only have a single product raised to its stoichiometric power divided by the multiplication of your reactants, where we have nitrogen and hydrogen. Of course, hydrogen is supposed to be raised to third power because that's the stoichiometric coefficient. So now, going to our A, for our first part of the question, for our A, we've been given half nitrogen plus 3H2 and what? Giving us NH3. So now, if I was to come up with a K expression for this one, what do we expect? So we're going to have NH3. On the bottom we have nitrogen raised to the power 1 over 2. Then hydrogen raised to the power what? Hydrogen raised to the power 3. So now, what have you noticed? How basically is this equation different from the one that we had on top here? So basically for the hydrogen there, it's basically a 3 over 2. I'll put that, it's 3 over 2. So what is the relationship if you compare the actual equation that we had and the one that we've been given in part A? What is the difference? So basically, ultimately, I would say it's like we had to multiply by 1 over 2. Okay, it's like we had to multiply by 1 over 2 this other equation, and that is basically what got to happen there. So now, after multiplying by 1 over 2, we've basically seen that it's like we were finding the square root of this other K constant. So what am I trying to say? I'm trying to say, if you try to compare these two equations that we've come up with, look at it. For the numerator here we have 1, there we have a power 2. On the bottom there we have 1 over 2, there we have a 1. Then the other part here you have 3 over 2, there you have like just a 3. So it's like 1 over 2. So what is that supposed to mean? What is that telling us? So if we are to equate this to what we have in the actual part, it is supposed to be K itself, the values that we have, raised to the power what? Raised to the power 1 over 2. So that if you multiply the 1 over 2 with what we have, or basically, or in short, what should we multiply with what we have for us to get to have the actual value of K there? So what you're going to notice is, what we're going to have for the first part, it will just involve us what? Raising our K to the power what? The power 1 over 2. And that is basically what we were trying to say. Because we've seen that. We have a 2 there, here we have a 1, 3 over 2, there we have a 3. So it's like that actual value of K must be raised to the power 1 over 2. so that it gets to give us what we have on the left. And therefore, whatever you get to multiply with any given equation, basically in this case we've seen that we multiplied the initial equation by 1 over 2, and after multiplying by 1 over 2, our value k for the question in A is going to be the actual k raised to the power what? The power 1 over 2, which we had multiplied with. Okay, so that is how we are going to find your value k. So if at all we had multiplied the entire equation by 4, we would have raised our constant there, the power what? The power 4. Now we multiply by 1 over 2, we are raising it to the power 1 over 2. So we are going to have 1.3 by 10 to the power negative 2 raised to the power what? To the power 1 over 2. So grab your calculator there, 1.3 by 10 to the power negative 2 raised to the power 1 over 2, or 0.5. Okay, so what value are you getting? So I'm getting a 1.14 times 10 to the power negative 1. That's my constant for the first part. Okay, let's go to the second part for B. For B, what has happened is we have 2 NH3 giving us N2 plus what? 3H2. So this is like we've reversed our equation there. And if you come up with a K expression, it's going to involve the multiplication of nitrogen and your hydrogen, the power 3, over what? NH3, the power 2. So now if you compare this with the actual one, it's like we've just like reversed. It's like the reciprocal. What is the numerator there is basically what? Is like now the what? The denominator. So basically that's what we are saying. We deal with a reciprocal. Whenever you reverse a reaction, and that is because we've reversed it. In this case, we are talking about our reactant to be what? To be the product in the other case. So we've reversed the actual equation. So if you reverse an equation or a chemical reaction, the K basically becomes the reciprocal. So for our B, it's going to be 1 over the actual K, which is going to be just 1 over what? 1.3 by 10 to the power negative 2. Okay, that is going to be our value of K for what? For the second reaction there. So we have 1.3 by 10 to the power negative 2 divided into what? Divided into a 1. So I have 7.69 times 10 to the power 1. Okay, so which is basically just 76.9. So that is for B. Going to our C, what has happened to the equation in comparison to the original equation? What has basically happened there? So we have 2 nitrogen gas plus 6H2, 4 NH3. So if you compare this equation with the actual equation, what do you think has happened there? So it's like we've multiplied that equation by what? It's like we've multiplied that equation by 2. It's like we've doubled everything. So what happens if you get to do that? So our value of K is basically going to be, it's like we have NH3 now. So the power 4, the N2, the power 2, it's like we're just like squaring everything. The power 6. So it's like we've squared the actual K. And I did mention that whenever you get to multiply any coefficient by the actual equation, basically that is going to be the value of your K as well. So it's going to be our K that we had in the first equation, the power 2. Why the power 2? Because we've actually doubled the actual equation that we had. So that's what we're going to have. So we're just going to square 1.3 by 10 to the power negative 2. Then we say what? Squared. 1.3 by 10 to the power negative 2. Then squared. So we have 1.69 times 10 to the power negative 4. So that's what we have for this question, and we are done. So in summary, what I've said is, whenever you've been given, or you notice something about the equation that you've been given, the new equation. So if you notice that it has been multiplied by a stoichiometric coefficient, a certain value. So for example, if the actual value is k, if your new equation is multiplied maybe by 1 over 2, for example, if you look at the first part, if it's multiplied by 1 over 2, then your new k is going to be the actual k raised to the same power. And that is what we did even for the last one. We had noticed that that equation is kind of multiplied by what? It's doubled. So you get to raise the k to the power 2. In a case where you reverse the equation, it's going to be reciprocal. That is the way to go about it. So what happens if you reverse and again you double it? It's going to be 1 over what? K squared. Question 4. At a particular temperature, a 2-liter flask at equilibrium contains 2.80 by 10 to the power negative 4 moles of nitrogen, 2.5 by 10 to the power negative 5 of oxygen, 2.0 by 10 to the power negative 2 of what? Of nitrogen, N2O. Calculate K at this temperature. So the given equation that we have is basically that reacting with oxygen to give us that product. Okay. So now from this equation that we've been given, we're able to come up with an expression for our K. So our products, we just have N2O raised to the power of what? 2. Our reactants, we have nitrogen to the power 2 and our oxygen to the power 1. So we are looking at the stoichiometric coefficients. Those are the ones that are becoming the powers. So now, what are they saying for the first part? So we're trying to find now the K. Okay, so we've been given the equilibrium concentrations. So basically those are just the number of moles. So we now need to come up with what? The concentrations themselves. So I'll start with the top part. We need to put the concentration of this reactant, of that product, sorry. So if you look at our product, it has been given to be 2.00 by 10 to the power negative 2 as that. So we need to put concentration because we deal with concentrations in our calculations. So we are therefore going to divide the given number of moles, 2.00 by 10 to the power negative 2, divided by what? The volume. The volume of the flask was a 2 liter. So put 2 liter. So if you divide that into that, what are we going to have? So basically we're going to have a 1 by 10 to the power negative 2. So that is going to be raised to the power 2 divided by. So we even shift now to the other part where we get to look at the nitrogen gas. So for the nitrogen gas, how many number of moles were we given? So if you look at the number of moles of a nitrogen gas, basically given to be 2.8 what? 0 times 10 to the power negative 4. So if you divide that, 2.80 by 10 to the power negative 4 over a 2 liter, our concentration is going to be what? So our concentration for our nitrogen is going to be 1.4, 0 by 10 to the power negative 4. Okay. So you do the same for the oxygen. For the oxygen, we are given 2.50. Divide that by 2, we have 1.25 times 10 to the power negative 5. So we've done our calculations there. We've substituted in the K expression. So we need to now just do our calculations correctly. Then we get to find our value of K. So after doing our calculations there, 1.40 multiplied by 10 to the power negative 4, which is part of a denominator, multiplied by 1.25 10 to the power negative 5, which is also part of a denominator. Then dividing this, we need to divide it into what? Into our numerator. So I'll do that. So remember, this is supposed to be squared. For the nitrogen, that is supposed to be squared. So after doing my calculations, the value of my K that I'm getting is basically 4.08 by 10 to the power 8. So that is my value for K in this case. So we've answered the first part of the question. The second part of the question says, if nitrogen gas concentration is what, and for the product it is what, for the oxygen it is what, does this represent a system at equilibrium? So basically our calculations are going to be based on the information given. So we try to determine the K. If it matches up with the one given from the equilibrium, then we are going to say it was at equilibrium. If it doesn't match up, then it wasn't what? The system was not at equilibrium. So let's get to do our calculations. So we have our K, of course, being dependent on the equation. So our product is N2O to the power 2 divided by our reactants. What we have? So for our reactants, we have our nitrogen gas, the power 2, and also our oxygen gas there. So we need to substitute now. For the product there, the concentration has been given to be 0.200. So squared divided by, for our nitrogen, we've been given to be 2 by 10 to the power negative 4 squared. For oxygen, 0.00245. Okay, so after doing our calculations there, what are we going to have? So I'm basically getting 4.08 by 10 to the power 8, so which basically matches up with our given our given K value at equilibrium. So the system was also at chemical equilibrium in the second part of the question. Question 5. The equilibrium constant is 0.090 at 25 degrees Celsius for the reaction that. So let's write that reaction that we've been given. So we have water, gaseous state, plus that. So by the way, a chemical equilibrium which involves all your reactants and your products being in the same phase, for example in this case all of these are in gaseous state, is referred to as homogeneous equilibrium. Okay. So now, for which of the following sets of conditions is a system at equilibrium? For those which are not in equilibrium, in which direction will the system? So in which direction will the system shift? Okay, let's get to do our calculations. So we basically understand that our equilibrium constant can either be given in terms of concentration or in terms of pressure. So therefore in this case our K is going to be, for our product we just have one, HOCl. Reactants we have water. So notice that I'm using different brackets because I'm dealing with what? Pressure and not concentration. But this is only applied to concentration. So I've raised the products to the power 2 because of a stoichiometric coefficient given. I'll start with my A. For our A, we only have one ATM for everything. So we have 1 squared over 1 multiplied by 1, which is going to be a 1. So now the question is the given 1? Or of course, actually, let me even change. Let me consider my K to be a Q, meaning that we're just looking at the constant at any point in the reaction. So in this case our Q is 1. So now, is 1 greater than the actual equilibrium constant 0.09? Is it greater or less? So we've seen that basically 1 is greater than what? 0.09. Or we're trying to say our K is basically what? Or our Q is basically greater than what? Our value of K. So what happens if we need to to make the two equivalent. Since we want to make this smaller so that it goes to the equilibrium constant, what do we need to do? So remember, if you increase the reactant or the product, sorry, if you increase the product which is part of the numerator, the value of Q is going to go higher, but we want it to become lower so that it goes closer to 0.09. So we are supposed to increase more of what? Increase more of the reactants. So for that to happen, the reaction is supposed to shift towards what? The left. So it's going to shift towards the reactant. So more reactants are going to be produced so that the value of Q reduces. Okay. So let's try to look at the second one, which is B. So plug in for our products. We have 21. So squared. For our reactants, water, we have 200. Then for the other reactants, we have 49.8. So grab your calculator there. 200 multiplied by 49.8. That should be divided into 21 squared. So the value that I'm getting is, I'm getting a very small value, and the value that I'm getting is a 4.427 by 10 to the power negative 2. In terms of a decimal number there, what I'm getting is 0.044. So this one becomes less. It is basically what? Less than K. So I would want to make it bigger. How do we get to make it bigger? How does it become bigger? So our value of Q in this case will have to become bigger if we get to favor what? If we get to favor the product. So that, because we do understand that if you look at our formula for our Q or our K, we are looking at what? The products. Okay, so the products, of course, raised to their stoichiometric powers divided by what? The reactants also to their stoichiometric what? Powers. So if we need to increase the value of Q there, we have to increase what? The numerator on the right hand side, which is representing what? The product. So in this case, the reaction will shift towards the right to produce more of the products. Then finally, for C, what do we have? So for our product, we have 20 squared over our reactants, we have 296 multiplied by 15. So 296 multiplied by 15, divide that into 20 squared. So here I'm getting a value of 0.090009. So approximately that is equivalent to the actual value that is given there. So in this case, we can therefore just say the system is what? It's at equilibrium, because the value of Q is the equivalent to the value of what? K. So there it is at equilibrium, so there will be no shift in direction. Question 6. At a given temperature, 0.3 mole of nitric oxide, 0.2 mole of chlorine, 0.5 mole of chlorine nitrogen oxide, gases were placed in 25 liters container. The following equilibrium was established. So our actual reaction is represented by this equation. Okay. So we are told that equilibrium we had 0.6 mole of that. So calculate the equilibrium composition of the gases. Determine the Kc for the reverse reaction. Calculate the Kc for the above reaction itself. Okay.